In this video, I'm going to focus on the deformation of solids, set 1 questions provided in class. Good news is you can ignore question 1, as it's no longer on the syllabus. Question 2, the key point to realise is that the area under the line, this part, represents the strain energy, which is the same as elastic potential energy. If you remember, that's the area under a force extension graph. So one of the ones you've just got to know, the answer's A. Why is that? Well, remember, if you do force times extension, if you think about the units, that's newtons times meters. You might remember another equation similar to this, work done. It's force times distance moved, or newtons times meters, which tells you that's equal to the joule. So the area under this graph, which would be a half Fx, as it's a triangle, is equal to the strain ng, or the elastic potential ng. Question 3 plays off that same idea, that the area under a force extension graph, although watch out because that's in centimetres, it needs to be in metres if we want the answer in joules. We also know the original length was 1 centimetre. So if its length goes from 2 to 3, that's effectively an extension of 1 centimetre to 2 centimetres, as its original length was 1. So that's going from here to here. So now we can use the equation I mentioned previously. The elastic potential energy is equal to half Fx, and just do that for it when it's at an extension of 2, so that's 4 newtons, times by 2 centimetres in metres, I've divided that by 100, minus a half times 2 times 0.01. So we're just doing this part here and this part here. Or, if you want to, you can work out the area here by splitting it into a triangle and a rectangle. Just a reminder to be careful with the units. If you count that into a calculator, you get 0.03. Next question asks us if we want to determine the Young's modulus. In which row can the measurement not be taken directly from the stated apparatus? So area of cross-section of a wire from a micrometer screw gauge. Now the key thing here is that's going to give you the diameter. So it's not going to give it direct. So that's likely the answer, but let's just check. Yes, this one you can use vernier scale to get the extension because that's the length. Electronic balance will give you a mass, and a meter rule will give the original length. So yes, A is the answer. Question 5. It asks where would the elastic limit be found. Now what's happening here is a force is applied and it's extending, obeying Hooke's law in this region, as F is proportional to X. Then it reaches the limit of proportionality, that's this point. That's not the elastic limit, so it's not that answer C. But we do know that it's going to be somewhere after that in this region, so likelihood is this is the answer, because it can't be that one, and it's not at T either. The way to find it would be by experiment. And you can tell it's past its elastic limit because when the force is removed, you can see the way it returns and finishes here with this permanent deformation. So that there represents that length that we'll never get back. So the spring might start like that, then we apply the force, it goes down to here, remove the force, and it ends up like that. And that there represents that there. Question 6. Tough question, this one. The first thing to realise is that they are talking about stress. Now, if you remember, stress is equal to force over area. The next thing we notice is that tension is constant. So we know that this is constant. Force, tension is a force. So we need to think about how the area is affected by thickness. We want half the stress. We want this to be times a half. So what change do we need to make to area given F is constant, and they are inversely proportional? So, what area are we talking about? Well, it's this little area here that it refers to, the cross-section area of this bit. If we look at it, something like this. This here is the radius, and thickness is W, but we know that W is a lot smaller than the radius. The radius is way, way bigger, which tells you up there. Now, if we want to work out the area of this, well, it's going to be pi r squared minus pi r minus w squared, because that will give us the distance from there to there. So we're working out the area of this whole circle, this whole thing, that's pi r squared, and we're subtracting it from the area of this inside circle, that's this part here, pi r minus w squared. Let's start by expanding out this bracket here. It's going to be a bit messy, so I'm going to just move down here. We've got pi r squared minus pi r minus w r minus w. When we expand that out, we're going to get pi times r squared minus 2wr plus w squared. If you can't remember how to expand that, quick recap of the maths might be needed. I'm not going to do that here. Times out the pi, you get pi r squared plus 2 pi wr minus pi w squared. Now, the key thing here is that we know that w is much smaller than r. So, first of all, we can see that these two just cancel, it's one minus the other, but we can also just ignore this term because w squared will be tiny or compared to this term here, because we're told that w is a lot smaller than r. This is quite a good physics trick. If we know that, w squared is going to be tiny, tiny, tiny compared to this term. So really, it's just that term there. The area is just 2 pi wr. Probably accurate to 5 or 6 decimal places. Now, the key beauty of this is that 2 pi and, what is it, r, because we know that the diameter is constant, so we know that r is constant. So we know that A is proportional to W, the thickness. So we know that this A here, cross-section area, is proportional to W. So if we want half the stress, we're going to need 2 times the area, which tells us that we need 2 times W. We've got our answer. A lot of work, admittedly. You might be able to go, no, there's not much shortcuts here. That's probably the best way of approaching that. In this question, we want the ratio of the stress in the wider part, so this part here, to the thinner part there. A reminder that stress is force over area. And you see that both are experiencing the same force. So we need to realise the idea that stress is inversely proportional to area. Now, if we double the diameter, so this is 2d, this is d. So if we have twice the diameter here, we're going to have 4 times the area here compared to here. That's cross-section area, that's that part there. Reason being, this is a circle. Area is pi r squared. Remember, radius is directly related to diameter. So if we double the diameter, we're doubling the radius. We square that, so it's 4 times. So we have 4 times the area. So if we have 4 times the area, we're going to have a quarter of the stress. So we've got to realise that this part here is going to have a quarter of the stress experienced by this part here. And that gives you your answer, because if the stress in the wider portion is a quarter of this part, then it's going to be 0.25 as the answer. They like that idea of pi r squared giving you the diameter. Just remember, if you double the diameter, you're timesing the area by 4, and then go from there. So this question asks for the strain energy, or the elastic potential energy, which is the area under this graph here. Now, you could integrate to find that, but we don't have the equation for the line, so we can't do that, and we're not expected to integrate for AS Physics. But remember that we do know that this is approximately a triangle, if we draw a line there. So the area under this graph is half fx. Don't forget to turn the 2 millimeters into meters, so 0.002 meters. If we do half times 100 times 0.002, we get 0.1 joules. So you might be tempted to go for B at this stage, but the key idea is that there's a little bit more that we haven't taken into account from our triangle, this area here, which would mean that the value is slightly larger. So the answer is going to be C. We know it's not D, because that would be the area if we didn't half it, if we just did 100 times 0.002, so that would be as if this whole part was under the line, which it isn't. So we know it's not that large, so the answer is C. This asks you to get the Young's modulus, E, from this stress-strain graph. Remember, Young's modulus is equal to stress over strain. And we see we've got stress on the y-axis, so it's the, change in the y-axis over change in the x-axis, which is the gradient of this line here. So we just need to do 2 times 10 to the 6 divided by the strain. Now you might go, this is a bit strange, it's in percentage, but remember strain is just a ratio. It's the extension over the original length. So it is unitless, or it can be written as a percentage. I'm going to turn that though into its its decimal value, which would be 0.01, because obviously we can't put a percentage into there. So I've divided by 100, and that gives me 2 times 10 to the 8, or D is my answer. This question here goes back to the first topic you will have done around uncertainties. So remember, Young's modulus is stress over strain. Now stress is force over area, divided by strain, which is the extension over the length. So if we write that neatly, we get FL over A delta X, or X, which is extension. Now, remember, when you times or divide, you add together percentage uncertainties, and these are already in percentages, so that's great. Then the slightly annoying thing is that we've been given diameter. Remember, area is going to be pi r squared because it's a steel wire, so the cross-section area will be circular. So therefore, we take into account the fact that the radius, which is directly related to the diameter, is squared. Now remember, when you square something, you have to times the percentage uncertainty by that value. So we get 3% for the area uncertainty. Now the rest are just as they are, so load is F, length is L, extension is delta X. So now we can just add together all these percentage uncertainties. So 2 plus 0.2 plus 3 plus 1. So 3, 4, 5, 6. That gives you 6.2 as your answer. So just be careful, remember that diameter is not area. So you have to square that, or square the radius, which is related to the diameter. Remember, when you square something, you times the percentage uncertainty by 2. Now, this question probably wouldn't get asked these days because it touched on stuff that isn't examined anymore, but you can answer this. Hooke's law is obeyed for all values of stress up to a breaking point. Well, for Hooke's law to be obeyed, we expect either a force extension graph to be a straight line or a stress strain, because remember, stress is proportional to F, strain is proportional to X. So we'd expect that to be a straight line as well. So yes, that is true. Let's check the others. Glass isn't ductile. Ductile means when you pull it a bit like a plastic, it kind of stretches out, or some plastics like blue tack, and extends before breaking. Glass is actually brittle, as you know, if you put a football through a window. But anyway, you can't tell that from this graph directly anyway. The glass shows plastic deformation. No, it doesn't. Remember, that will always happen after it stops being directly proportional, past the limit of proportionality. There's no evidence of that there. Then ultimate tensile stress is basically the ultimate stress it can take. And that tends to be constant anyway for a material. Not always, but very likely would be. So, and to us, we can't even see this from the graph, so that's not right. So the answer is A in this case. So a bit of a repeat of previous questions. Again, it's asking for strain energy, which is elastic potential. Reminder, that is the area under the graph. Just a bit of a pain because it's not a straight line. So you're going to have to do some sort of counting squares. And it says what is the best estimate. So it's up to you how you do this. You could take one big block and work out how much, what the area is of that block. Just remember, this needs to be in meters. And then you can count those big blocks and estimate how much of these add up to a block and go from there. I'll let you do that one, but you should get an answer of A once you have done that. Just be careful with the centimetres into meters. Ultimate tensile stress of a material. Well, the Q's are in the name. Stress, you know what that is. Ultimate tells you it's the kind of final one before it breaks, and tensile tells you it's a tension force. So basically, to find that, you get your material, apply a tension force, and see what stress it takes just before it breaks. Now, let's read them over. The maximum force that can be applied to a bar of the material before it bends. No. The maximum interatomic force between the atomic bonds of the material break. Yes, but I mean, it's kind of touching the idea, but it hasn't talked about area, and stress is specifically force over area. Maximum stretching force per unit cross-section area before the material breaks. Yes, hello, that sounds good. Answer C. The maximum tensile force in a wire of the material before it breaks. Almost true, doesn't mention area, so no. Question 14. So this asks for the work done, which will be equal to the elastic potential energy or strain energy stored in the material. from 0 to the extension 12. Simplify the calculation by treating the curve xy as a straight line. So I've helped you out there, and they say you can treat that as a straight line. So again, total, if we know the total work done will be equal to the energy stored in strain energy, which we know on a force extension graph is the area under the graph. So you need to work out the area of this triangle here, this rectangle here, and this little triangle here. Add them all together, and you should get B when you do that. I'll leave you to do that one. Question 15. This one, you've got two springs in series. We know K1 is 4,000, because it's kilo, newtons per meter. And we know that this one is 2,000 newtons per meter. Now we know the load is 80 newtons. Both springs will experience that load because since they're in series. So we can work out the extension using the equation F equals Kx. X equals F over K. We can deal with each spring separately. So let's start with this first one, K1. If you do the force of 80 divided by the 4,000 K, you're going to get 0.02. That's in meters, which if we times by 100 tells me it's 2 centimeters extension. Then you can do the same again for this one, but you can also spot it's half the K, so we're going to get twice the extension, so we should get 4 centimeters extension. So this extends by 2, this extends by 4, so the total extension will be 6. So for this question, they've given you the equation, which is nice of them. That just comes from Young's modulus is stress over strain. They've given you some measurements, and they've given you their values with their uncertainties. And they've asked which one has the largest effect on the uncertainty of the Young's modulus. And again, this goes back to what you have done at the start of the year on measurements. What I've done is calculate here the percentage uncertainty by just dividing the absolute uncertainty by the value and turning it into a percent. The only difference is for diameter, as we discussed earlier, because diameter is squared. The uncertainty in d squared, you have to double this divided by this, because if you square something, you have to double its uncertainty. That's just a rule we've got to follow. So if you went for d, that's what you forgot to do. There's a trap there because otherwise d is the largest. But if you double it, then b becomes the largest, and thus that is your answer. This goes back to a bit of stuff you did in GCSE and some other ideas, just knowing how materials behave. Let's start with 2. 2 is quite an obvious graph to spot because of this kind of SE shape. And this is for anything that's sort of rubber or elastic bands, which are made of rubber. So anything kind of made of rubber or some sort of certain plastic. So we know the answer 2 is rubber. Let's work out which one's glass and which one is metal or copper. Now, both don't experience, when you apply a stress, they don't extend much. So you get this very steep line initially, which tells us it's very stiff. So both of those are. If you imagine pulling glass, it doesn't really extend. And you imagine pulling a metal, it doesn't really extend. But then you should know that metals eventually kind of yield after a while and kind of give you quite a bit of strain just before they break. So they actually extend a little bit, quite a bit. If you ever pull a kind of metal wire, eventually it does kind of give. Whereas a glass isn't going to do that, it just breaks because it's brittle, as we discussed. So this is glass, and this is a metal, so the answer is B. This question, again, we've got a load extension graph. A bit of a difference here because that's not force. The force would be the weight, so we can times this by 9.81 to turn it into newtons. Extension, again, in millimeters, so don't forget to divide by 1,000. How much work is done? Well, work is done is going to be equal to the elastic potential energy stored, or the strain energy stored. And it wants it increasing from 10, which is here, to 20. Careful to read off the points accurately. That's not 2 there. It's going to be just shy of 2 at about 1.9. This one I would say is 3.8. So what you've got to do, which is a bit tedious and I'll leave you to do, again, is find the area under this graph. You could divide it into a rectangle and a triangle. Or, if you wanted to, you could work out the elastic potential energy at this point using the equation E equals a half Fx. Reminder, you've got to times this by 9.81 to turn it into a force. You've got your extension there. And then you could subtract it from the elastic potential energy at that stage. So here you'd put in your 20 divided by 1,000. minus half fx for this part, where you put in 10 divided by 1,000 there. I'll leave you to do that. And you should get an answer of C if you do it correctly. Notice the little trap here. This will be if you don't convert your units. So turning load into newtons by times by 9.81 and converting extension into meters by dividing by 1,000. So this question asks you for the behaviour of the metal between X and Y, which is here. Now, temptation is to say, look, it started curving off. It's past its limit of proportionality, which a lot of people get confused thinking that's the elastic limit. It isn't. We don't know where the elastic limit is on this one. You'd have to do an experiment to find it. It's not where the limit of proportionality is. The limit of proportionality just tells us it stopped being a straight line and force has stopped being proportional to extension. So it stops obeying Hooke's law. That's all it tells us. Now, the key bit of information here is that the sample contracts, it follows the same curve as it was stretched. So basically, when you remove the force, it goes back along this line and ends up back here. Well, if it ends up back here, that tells you that there's no permanent extension. What would you expect to see if we removed the force and there was some plastic deformation? We'd expect it to go along a line something like this, and you'd have this permanent deformation, this permanent extension that you can't get rid of. But it doesn't. It tells you that in the question. It tells you it follows the same line, so we know that therefore it must be D, because there is no plastic deformation. It's not plastic, so it's definitely not that one. It can't be neither. It's got to be one or the other, and we've just said it's not plastic, so it's not that one, so it's got to be that one. So it's elastic deformation because it returns to its original length, because it tells you here. This question asks for the spring constant. Reminder, the spring constant is in the equation F equals kx, Hooke's law. K is equal to F over x. Now, it's a bit annoying here because what they've done is they've flipped the axes. Normally you'd have F or load up on the y-axis, and therefore it's just the gradient. So just watch out for that. That's fine. We can just find the change in F divided by the change in x. Because it's a straight line, we know it's obeying Hooke's law in this equation. So if that's 0.1, this will be 0.2, 0.3, 0.4. So we know the change in the force is 0.4. That's this part here. And for that change in force, we get an extension of 5 centimetres, which is 0.05 metres. Type that into your calculator and you'll get A as your answer.